So far, we talked about node embeddings. Now, what happens when you have a database tuples? And in principle, you can say, well, in the usual representation of a database as a graph, tuples or facts become the nodes. So we can simply use the node embeddings. Well, this is true, but remember that in the node embedding techniques that we've been discussing, we are all using only the graph structure, only the essentially the edge information. But when converting databases into graphs, there is additional information. In particular, we have the labels, which are the relation names, and we have the content. And we're going to discuss two approaches that essentially use this information. One is extending node embeddings to heterogeneous graphs, and we're really going to use just the labels of the nodes. So it is really a way of embedding nodes in a label graph. And then we're going to discuss database-specific embeddings that actually look at the attribute values. Okay, so let's start with node embedding in label graphs. So we have a heterograph schema, and remember that it includes set LV of node labels, a set LE of edge labels, and a mapping M that to each edge label associates a source label and a target label. Okay, and also we have D that maps every node label into a dimension. We're not going to use it now. Okay, this is a concept that is often used in machine learning over structured data when we have databases, and that's the concept of a meta path. And this is basically, think of it as a schema of a path over the heterograph. What does it entail? It includes labels of nodes, a sequence of labels of nodes, connected through corresponding edge labels. Okay, now I mark it here as undirected because edges can go in both directions. So formally, each sigma I is a label in LV, each tau I is a label in LE, edge label, and M of the edge label tau I is sigma I minus 1 comma sigma I, or the other direction, sigma I minus 1. Okay, so this is the idea, very intuitive. Okay, so if this is our heterograph, then we can think of our meta path as extracting information like student connected by TS to take and going back by TS to student. That doesn't say much probably. But this one is more interesting. A student connected to take by TS, connected to a course, and this is another, possibly a different student taking that course. So that represents an interesting relationship. Okay, so from metapaths, we get this idea of random walks over a metapath. So suppose that we have a heterograph over heterograph schema. I'm not going to remind the definitions. It's not critical now. What we need is to understand that if we have an undirected path, which is basically a sequence of nodes from the graph, then it conforms to the metapath phi if, well, basically what what the intuition says. The label of every vi is sigma I, and there is a tau I edge either from vi minus 1 to vi or from vi to vi minus 1. It basically means that, the schema of this path is the meta path. Okay? And then a random phi walk from a node v0 is basically obtained by choosing a random path corresponding that conforms to the meta path. Okay, we start with v0, And then for each I, we choose VI by choosing a uniformly at random sigma I node, okay, by connected to VI minus one that we chose previously through some tau I edge. Okay, so really following the path, but whenever we encounter a new edge, we select randomly from our choices. Okay, so here are some ways of using metapaths for node embeddings. Okay, and this is a general way, or metapaths are generally useful in extending techniques, machine learning techniques over homogeneous graphs to heterogeneous graphs, and specifically in the case of embedding. Let's look at examples. Hint to vec, hint meaning heterogeneous information. Okay, so basically they said, okay, let's use this self-supervision idea where for two nodes U and V, we would like to have a classifier to build a classifier using the embeddings, telling or testing whether there is a um, phi path. There is a path from U to V conforming to phi. Okay? And then they define this classifier based on the probability estimator that uses an embedding of U, an embedding of V, right, as expected, plus an embedding that is specialized to phi. And then you can use several phis. So this is one approach. eSIM basically says, let us define a probability distribution for every phi between pairs of nodes. So think of it really as a random process going from U to V. So the probability of V given a U is basically uh, it is defined as an expectation or exponential, sorry, over this function f, which is defined as follows, normalize. Okay, so this is basically the decoder. The they train it on the actual random phi walks. Okay, so they apply this phi walk, they use it as a Markov process, and then they try to learn this Markov process through this, or to estimate this Markov process through this probability function, which involves the embeddings. Okay, so what are in these phis? Well, the embedding of U, the embedding of V, the dot product of them, and plus parameters that are um, fitted or correspond to phi. Okay, so this is the idea, and from that they get the embeddings of the nodes. So that's another approach. Okay, the Markov process. Here's another approach: metapath to vec. Basically, think of it as node to vec, but now you're not considering a, arbitrary path, but just paths that correspond to a specific metapath. And again, you can use it with several metapaths. And using, again, the idea of negative sampling for scale. Okay? So basically, well, you can see in this pseudocode that there is some gap in our terminology. We call metapath, they call metapath scheme, and what we call a random walk, they call a meta path. But up to that, think of it as follows. You have your meta path in this the constraint or input of the learning algorithm. You choose a random walk, and then basically you just do the usual thing, skipgram, where in the skipgram you go through windows, and whenever you see a new node, you basically compute your probability function and apply um, a step of a stochastic gradient descent. Okay, that's the usual thing we see in a skipgram. Now they tried their algorithm on this scientific publication data set A minor, several millions of papers and thousands of computer science venues. And they try it on node clustering. So they start with the real labels, giving several clusters of papers or venues and authors. And they compare the clustering that they get by first embedding and then clustering the vectors that they get from the embedding to the original clusters. What they show is basically that the metapath approach, the heterogeneous approach, is really getting much better results than the heterogeneous, the homogeneous node-to-vec. So this is interesting. Okay, and for clustering, they use NMI, normalized mutual information, that basically measures the correlation between two clusterings. Now, this is the diagram, the TSNet that I showed at the beginning of this module, where they basically visualize in 2D the different conferences. And you can see that indeed conferences of a similar topic are mapped next to each other, which is interesting. Okay, so next we talk about embeddings that are specialized relational databases and use the attributes of these databases.